Okay, we're going to use the formal definition of a limit to show that the limit of 5x minus 3 is, as it approaches 1, is equal to 2. Okay, and we're going to set x naught. We're going to set x naught as equal to 1, and we're going to set, and f of x is obviously the function right there, and L is equal to 2. So the limit is equal to 2, because that's what it is. Now, for any given epsilon that is greater than 0, in order to prove this, we need to show that we have to find a suitable, for a given epsilon that is greater than 0, we have to find a delta also greater than 0. We're going to find a delta that is also greater than 0, that if x is not equal to 1, and x is within the distance of delta from 1, meaning this, okay, meaning that if it's greater than 0, if this is greater than 0 because it's not at 1, we're getting closer to 1, and it's within the distance of delta, then f of x is within a distance of epsilon from the limit L. That is f of x minus 2 is less than epsilon. So we're basically saying, pardon my cough, we're basically saying that in order to show that this is a limit, we need to show that there's a delta value. We need to show that there's a delta value that x naught can stay within, that shows that the distance from x to x naught can stay within. That also shows that the distance from f of x to the limit can also stay within epsilon. And the way we do this is by using the formal definition, and we work back to find the delta by working back from the epsilon inequality. So we say, this is the epsilon inequality, so we say f of x, which is, 5x minus 3 minus 2 and epsilon, because that's what this is. And this is the same thing as saying 5x minus 5 epsilon, right? But this is also, we could also rewrite this as here. We could also rewrite this as being 5x minus 1 is equal to, it's an inequality. Okay. Now we're almost again to this inequality. We've got to get to x minus 1. If I do this, we can divide both sides of the inequality by 5. If we divide both sides of the inequality by 5, we are just left with x minus 1, then epsilon over 5. So there we go. We've got it to this inequality. So we could now assume that delta is this. Delta is this. This is what this would be. It would be epsilon over 5. Now we have to show that epsilon, given this, epsilon is f of x minus 2 is still within epsilon distance. And we can, by again doing this inequality, we could say that since we could do this inequality, we can go through the same steps, put the inequality in there, and when we get to here, it's still equal to epsilon, but we could say that this is also equal to delta, which is just epsilon over 5, delta, which is, again, epsilon over 5 times 5, because it was epsilon, and that's what this was, dividing it both sides by 5, which is just equal to epsilon, which shows that it still stays within epsilon while it stays within delta. And now, which shows that this is really the limit. If it didn't stay within epsilon, we couldn't find delta for it, then it wouldn't. It means that it wouldn't be getting as small, as the distance for this stayed within delta, as we kept getting smaller that we want, the distance that we wanted to stay within couldn't keep getting smaller, or couldn't stay within this distance that we wanted to, this error rate. Or the same thing vice versa. So we could have stayed within the error rate, we weren't able to stay within this this confine for delta. So yes, that's how we go through it. We need to find the epsilon. That when you find delta, the inequality for this still stays within epsilon. So yes, we've kept this, and that's how you find it. That's how you prove it. Okay, stay in school.